Hello, everyone. This work is done by Dr. Amir Saki, who is a postdoctoral fellow at the University of Quebec at Trois-Rivières, and myself. Okay. For this presentation, I give you I try to be as much brief as I can. So it's going to be two-part. The first part is the theoretical part of our causal model. And then the second part is a code that I'm going to go through the code, and I'm going to explain to you the results. So in this presentation, I'm going to discuss about our the causal inference, okay, the causal inference metrics that we created. So this causal matrix has some properties that, to the best of our knowledge, you cannot find it in other causal models. The first is that it considers the various types of treatment variables such as binary, categorical, and continuous, using total variation as a base and mathematical base of our model. Because in other models, usually they use different type of mathematical formula, but here we only use one, and then we can treat every type of treatment variables. Our model accounts not only for intervention in treatment values, but also for their rarity and frequency. Okay? And it also considers it, for the controlling of the rarity and frequency of treatment by introducing a degree D. And we also consider the rarity and frequency of covariates by introducing a degree R. And we have the gradient, which captures how the outcomes responds to infinitesimal interventions on the variables of interest. Therefore, since these outcomes change, result from deliberate intervention, and they are causal. The code that I'm going to discuss with you comes from this paper, Lundberg. It was on Medium. So maybe some of you who are familiar with causal inference, you already seen that. So I'm going to discuss about this code and what we added to this one. Okay. Very briefly, maybe most of you knows about causality. Causality is the science of cause and effect, focusing on how to interpret and quantify the impact of one variable on another when one actively intervenes. This means understanding not only that two variables are related, but also whether and how changing one variable will produce changes in another. That comes from Mr. Pearl. Here in this presentation, we want to find the causal effect of x on y, assuming y is equal to g, a function of x and z. Okay, I go back to the Robin Neimann's framework very briefly, with an example. Suppose a researcher wants to know if a specific pill is effective against lung cancer, for instance. The causal effect of the pill on cancer could be calculated as the difference between the patient's state in the following cases: taking the pill and not taking the pill. So basically, we can write causal effect as the expected value. For some of you who are not familiar with the expected value, this is the mean. Okay? The expected value of y do pill. When we write do, this is in causal inference, it means intervention that comes from Mr. Pearl, that I just gave you the definition of causality. So do, it means that we are fixing a value. We say to the patient, take this pill, okay, which is equal 1, which means that the patient take the treatment, equal 1, subtracted by the mean or expected value of y the patient does not take the treatment. So here we give the treatment, here we don't give the treatment. So basically, this is the fundamental problem of causality. Why? Because if we give the treatment, we don't know what happened. What would have happened if we didn't give this treatment, right? And if we don't give the treatment, we don't know what would have happened to the patient if the patient took the treatment. Okay? So this basically, this is the way that Mr. Robin solved the problem. Okay, so we come back to the AT, the definition of AT, average treatment effect. Okay, the AT aggregates the treatment effects across all subgroups weighted by the probability. I think this is a better way of explaining AT instead of writing the formula for some audience. So a summation of C, proportion of in the subgroup C multiplied by the treatment effect in subgroups. So if we go with the probability approach for this diagram, first of all, this diagram is a DAG, which means it means directed acyclic graph. What does it mean? It means that if I start from here, I cannot go back. You see, if I go from here, I can go here and I can go here, and there is no loop here, right? And if I go here also, I cannot go back. So that's why we call it DAG, which is introduced by Mr. Judah Pearls. So if I go with, and another things that I want to bring your attention to, the C here is influencing T and Y at the same time, right? So we call it the confounders, when one variable is influencing more than one variable at the same time. If we go with the Bayesian approach, so here we have probability of C because this is a parent node, then we have probability of T given C, and then for Y we have probability of Y given C and T. Okay, but this, as I said, this is the confounder. It has many problems. I don't want to go into details. We cannot do that. So what we do is that we use this do sign that Mr. Pearl introduced, which means that here we are deleting what is come to T, right? So we are getting rid of the ambiguity because this C is a confounder and makes ambiguity. So when we do T, which we mean that we are fixing T, okay? We are fixing T. Here you see that Y probability of Y given do T0, which means that you are fixing T. And then here we have the summation over all value of C, probability of C multiplied probability of Y given T and C and T0, okay, because we are fixing. Okay, so now if I write the expected value or the mean value of Y given do T0, which is fixed, I will have expected of the summation of Y multiplied by probability of Y given do T0 and C, right? So if I write, if I rewrite this one, I can write something like this. Here, since we don't have C dependent on Y, we can take it out of the these parentheses, and we can rewrite this one. So this becomes probability of C multiplied by the expected value of Y given C and T0. So basically here we deleted this dependency, probability of T given C, which caused the confusion. Okay, now coming to our, a little preamble for our model. So we saw that ATE, the formula of ATE, just explained. Now, there are two problems, big problems with this ATE. Let's say that our data set is something like this, very simplified that. So we have C1, these are subpopulations, C1, C2, C3, C4, and C5. Now, you see that the subpopulation C4 is small comparing to others, right? Now, if we apply this formula, the expected value of giving treatment and not giving treatment, when we make the subtraction for C4, we will have a very, very large number. Okay, and if we do it for another C or for the whole C, the same thing, you see that it's very small. So basically, the ATE that is introducing causal inference is not capable of accounting for this type of problem, which means that if my subpopulation is small, but its causal effect is very big, how can I calculate this? And this is what we are addressing in this discussion. Okay. Another things that we need to think of, and it is, if for some of you are familiar with, is the propensity score in causal language, is that the treatment. Okay, here I put the people on C1, under C1, the people who are receiving the treatment are smaller proportion of this C1, and here the people who are not receiving is T0. So basically, this is also another problem that in causal inference they solve it with propensity, but they try to equalize. But this is not correct because, as I said, when you have a small portion that has a big effects, we need to take to account for that. So we define two things: the degree R, it controls the rarity or frequency of each subpopulation. Degree D controls for rarity or frequency of receiving treatment within each population, which is here. Okay. So our model, we call it total variation. It comes from total variation. The base of our causal model is total variation. So we adapt it to different situation, and right now it's adapting to multivariate causal effect. So for univariate function, we have this a real valued function, okay, defined on a closed interval a and b. Okay, and we define a partition. The partition is, for example, between a and b, and we have x0, this partition until x and p. So here I showed it visually, so it's going to be easier for you. Here we are talking about different partitions, okay? So basically between A and B, we can have this partition, and then we can have also Q, you see? So we can have different type of partition. Why I'm saying? Because the total variation, it calculates the supremum, okay? The supremum, or for some of you who are not familiar with supremum, is the maximum value. Maximum value of all of these changes, okay? Between every elements, for example, x0, x1, x0, x2, x1, etc., etc. Okay. For the continuous variables, if f is continuously differentiable on the interval closed interval a and b, then the total variation is going to be something like this. So this integral represents the arc length of f when viewed as a curve in one-dimensional space. So the total variation measures the total amount by which the function increases or decreases over the interval AB. It can also be thought of as a total distance traveled by function's value as t moves from A to B. If we want to talk about physical terms, ft's represent the position of a particle moving along a straight line over time t. Then Vf is the total distance the particle travels between times A and B. For the discrete, as you can see here we don't have supremum. You see, if here I showed you that there is a supremum, here we just have the subtraction of availabilities. Okay. In order to make it a little more visual, you can see if these are our data points. Okay, here we have the absolute value of x1 subtracted by x0. If we go to this part, which is going down, right, it becomes negative, we have absolute value of x2 to minus by x1. Then what we added here is to this total variation is the probability of each event. Okay, we can write this by considering x0 and x1 are independent. Okay, when we are intervening in causal inference language. Okay, and how we added this degree D that I just discussed about, we added to the power of each probability. So because these are the frequencies, and then we can easily understand how it moves. Is that high impacts or low impact in the whole causal inference. So basically, our formula, which is the probabilistic variational causal effect with the degree of D, becomes something like this. We are calculating the maximum of these differences. G in here is the intervention. Okay, when we intervene on a node or an event, and then we make other variables fixed. Z here is fixed, and then we have this probability, this xi in partition P that I showed you above, and then G are the degree. It can be between 0 and 1. It can be the frequency of the events. Okay. For some of you who are more on the statistics side, I think this is going to be helpful. Why did we select D to the power? So let's consider D2 and D1. D2 is greater than D1, and they are both greater than 0. Here, what we have is that we are having on the denominator the availability of changes from xi minus 1 to xi, right? Z always fixed with degree D. And the denominator are the availability of changes from xj minus 1 to xj. Okay. And this, if let's say this one is greater than 1, don't forget about D2 greater than D1 greater than 0. So basically, we have the same thing here, but they just have D2 and D1. We can rewrite it like this. So if we have alpha to the power of D greater than 1, then alpha is greater than 1. So we can have this one, the whole formula greater than 1. What does it say to us? It says that the more frequent event we have, the bigger causal impact can be. Okay, that can be a justification for degree D that we added. Okay, but for the mathematical formula, I refer you to our paper that which is on archive. Okay, we can also consider D as a logarithmic function. We can also consider a logarithmic function to do the same. We can also consider weighting. Okay, here we have the weighting, a function that allows in order to control the D, which means rarity or frequency of the events. Okay, well, for the subpopulation, what we did is that we took each probabilities that I showed you and we put it on to the power of R and divided by A. What is A? Is the summation of all these probabilities. Okay, and we get for the Bayes probabilistic variational causal effect formula, we get this expected value that I can rewrite it like this, which means that we are taking the expected value or average of a function over the variable C. Okay, where C is sampled from this probability, okay, according to the adjusted probability distribution of this one. So basically, this approach ensures that our causal inference are not unduly influenced by the distribution of subpopulations, allowing for more nuance and equitable analysis. We also define the positive and negative variations. Okay, so basically the positive is going to be the supremum of the positive effects, and here the negative is supremum of the negative changes here, as you can see. And I'm going to show you in the code. And the final things that I think is very important here, we also calculated the mean piece formula. Okay, in the mean piece formula, what you see here is that we are normalizing the transition probabilities across xi and xi minus 1. Okay, by dividing to this. Okay, so we can define mean pace as well as other formula in our framework. I'm going to show you this. I wanted to explain this like that, but I think it's better that I show you the formula here and then give you some examples. So basically, with one total variation, we can come up with different version of our causal effect. Okay, so what are these? As I said, I'm going to explain to you, but by this example, the piece probabilistic easy variation causal effect, like what we can do with it, an example would be, imagine you're studying the effect of daily coffee consumption on energy level by measuring small changes, okay, 1 or 2, 1, 2, 3, and keeping other factors constant. Please assess the total impact of each incremental change weighted by the probability of each level. Well, since we don't drink more than 5 coffee usually per day. Okay, so piece measures the sum of small effects capturing the cumulative impact of all incremental changes. We have Bayes probabilistic average causal effect, studying the effect of exercise frequency on body weight by analyzing categories like no exercise, light, moderate, or intense. Bayes calculates the average effect on weight while emphasizing on the highest possible intervention effect. Okay. So this approach captures major shifts like the difference in body weight between no exercise and intense exercise. We also have another version of our formula, which is S by S, supremum probabilistic interventional variation and space. So example can be assessing how different levels of sugar intake affect blood glucose. So SPIV identifies the largest single intervention changes, the largest increase in blood glucose between specific sugar levels. So it aggregates SPIV values across scenarios like sedentary or active, providing an overall view of the highest interventional changes across setting. And finally, we have aggregated PIV, okay, or a PACE. So studying how increasing doses of medication impact symptoms relief. Okay, like this one sums the effects of all those changes. Okay, for example, from 10 to 20. and it aggregates these effects across groups, adults versus senior, offering a comprehensive view of overall causal effect across all changes in subgroups. So basically, we started from total variation, and we came with different version of this. Why? Because as you have noticed in these examples, we have different cases, different problems, so we should be able to use different formula in order to find the causal effect. So basically here we are going to this data set, okay, that is provided by Lundberg, Scott, and I checked their this data set created by these researchers. They were from, I think at that time they were working on Amazon, Stanford, and so this is something that is is a good data set to me. That's the reason I selected. You see something here. Before I forget, I wanted to mention. You see these dotted circles. These are the nodes that are going to be deleted from the data set. Maybe in the code I forget to tell you, but from now, just remember these two is going to be deleted. But we are going to see the impact of sales calls and how whether the customers renewed their contract. Okay, for example, they renewed for next year. Okay, so they wanted to see if which one is more important. Is what was the cause? The real cause, was that the discount they gave? Is it the economy of the client, or the spend advertisement they have seen, or monthly usage of the client? And as you can see, there are nodes that are missing. You are going to delete them. The code is in here in this GitHub repository. So here we have this file. As I think you saw that it says multivariable. So here I'm going to show you for one variable. The multivariable is a little more complicated. The code is there. You can see we did it for two variables here, and it can we are working on the code. It becomes for multiple variables. We just need to generalize the code. But if you like this presentation, and if you want it, I can make a presentation about multivariable. So here, basically, we are just going with one value. Okay. As I said, the code comes from the link that I showed you. So the first part of this this code is fixable data frame. Okay. Later on, if I can scroll down here, what this code does, I'm going to show you in the Okay, what it does, the code I just show you, is that it fixes the column. When we have a data set with 20 columns, what it does is that it selects some values. Okay, I'll come back to this one. So it fixes this value. We select a value and we fix this column, and we leave others unchanged. So basically, we're fixing this column, and then we are going to calculate the causal effect here, as you can see. Okay, so what this code is doing is that basically is just fixing a column. Okay, it's a dictionary. It's fixing a column, and it let us to do what we want. We want to do manipulation and doing calculation with with our causal effect formula. Okay. So what I just show you, just as a reminder, I just show you the sales calls interaction. So it's an NP uniform. I try to put some comments here, as you can see. For example, each number is sampled uniformly from the range between 0 and 4, as you can see here. Here we have interaction, which is influenced by sales call, as we saw in the diagram, right? And then we are introducing a little noise, okay, from this normal distribution. The value is between 0.5 and this one. For some of you who are not familiar, the noise we are using in order to make sure that our algorithm is enough robust, right? But one reason is going to be this one. Then we have economy. This one is not, economy is not dependent on any other variable. Here you see that if I just show you again, sorry for that, economy, you see that this is not influenced by any other variable. okay, and etc. So what is important is that the customer satisfaction, the Y that we are looking for, is this formula: 10 multiplied by 0.5, 0.3, 0.2, 0.1, etc., etc. So it's multiplied by all these columns. Okay, so if something that is important, because we are going to see the causal effect down here, when we apply 10 multiplied by 0.5, we have 5 here, right? We have 5, we have 3, we have 2, we have 1 and 1, and you see. So basically, the most important columns here for us are product need and monthly usage. Okay, 5, 3, and economy. The second one. The rest are really small. Okay, because these are right 0.2 multiplied by X sales. Okay. So here we are generating 10,000, okay, of these samples. I wrote you this formula also, the formula that which I just explained, 10 multiplied by this. So maybe this is a little more clear in case the above is not enough clear. Okay, so you can see these, and as I just mentioned, we are deleting the product need and bug face, because the in causal effect, as you know, one of the big problem is that somehow we have some elements usually that we cannot see, okay, in the environment. They are not in our data set, right? For example, bugs faced, we don't have data about these. Okay. So we use the first part that is again comes from the authors that I mentioned. They use the XGBoost, okay, algorithm. The XGBoost algorithm is tree based. So we are creating trees based on the previous trees, and each tree try to modify the errors in the previous trees. It's very brief explanation. I know it's not enough, but because I'm going to discuss about more and we don't have enough time. Anyway, just a tree-based algorithm. Here, I just put you the learning rate, the sampling, the maximum tree. The trees can go from 0 to n, and then here the objective function. Okay, here's the squared error. So basically, when we apply these, XGBoost, you can see that the result R2, okay, our R2 score is 0 0.96, okay, 90%, 96. And then they use Shapely. So the Shapely, what it does, basically Shapely was created for game theories. What it means that they wanted to see what is the a contribution of every element or every player in a game to understand the overall output of the system. Okay, so but in the context of machine learning, Shapley values are used to explain the contribution of each feature to the model's prediction. Okay, the formula here is that what we see the Shapley values of feature I. S here is subset of features, excluding the I. As you can see here, this backslash is excluding the I. S is the number of features subset, and N is the total number of features. Okay, here what we are doing is that once we are adding and once we are subtracting, and we'll see what is the what is the influence or what is the impact. Okay, so basically here we are having a weighting factor which ensures that fairness by accounting the number of permutations. Okay, so I let you look at these later on when you have time. When we are using Shapely, what it does is that it says that ad spend is the most influential element. Okay, with the XGBoost. Okay, and then it put last upgrade as the second element. Okay, let me just go up there and show you in the real data set. Okay, if you go here, these numbers, you see the most powerful, I told you, product need, which we deleted. Okay, you can see here, product need we deleted, it's not there. Okay, the second after that is monthly usage, and then economy. Okay, and then discount. Okay. But here, when we see this, okay, you see that ad spend is the most important, and then let's upgrade, and then sales call, right? This is the problem when we are using for example, machine learnings, okay, without causal inference. So if here something that is interesting is again this is the Shapley. So here this is small. These are the distributions. You see, these are uniform. Here we have two normal distributions or Gaussian distribution, and here another distribution. When we are talking about the Shapley, okay, the Shapley values, you can see here this is positive, 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 and here something a little, I would say, negative because it's going like this, and then this stuff. So Shapley is mostly, for me, it's a correlation. Okay, right? With the formula we have saw, because we don't have intervention in Shapley. The first thing that I want to explain here in this code is the marginal effect. Marginal effect explanation is that the marginal effect refers to the change in the outcome variable that is caused by small changes in the explanatory variable of or treatment variables, okay, while holding other factors constant. Okay, but a good example, very simple example, here we have y equal to x plus 5. Marginal effect, we are doing the partial derivative, and it's going to give me 2. Okay, so this means that every additional hour of study, the exam score increased by 2 points, holding else constant. Okay, so what we are doing here is that basically the marginal effect, first of all, it tries to see if this is, for example, our column, it tries to see what can be a representative value for the 0% of the whole column values. Okay, and then what here, for example, we have this value, and what is the representative for the 25% of the whole column value of whole column? Here, for example, is 1, and then for 50% or median is 2. Okay, so basically what we are doing is that we take one column in marginal effect, and then we are trying to find these percentage, 0, 25, 50%, 70%, and 100. Then what we do is that using the fixed code that I showed you up there very briefly, we are fixing this column with that value once, with the 0 percentage, 0.3, and then we are leaving the other values for other columns, and we are calculating this customer satisfaction. Okay, and then at the end we are taking the mean of these. Y is equal to the mean of these, which is 5. Okay, so we are doing once for this one, once for this, and once for this. Okay, for these 4 values, which are the representative, and we are calculating the mean, and we are obtaining these mean customer satisfaction. So this is what marginal effects doing. Okay, basically what we are done is that in my presentation I showed you we intervene. I told you we intervene. We are fixing the values. Well, it's fixed, and then we are calculating the changes, and we say that what is the causal effect. Okay. Here is the code for marginal effect. As you can see, we are initializing an empty list of lists, and then for each column, the corresponding feature values are extracted, okay, and sorted, and then we are having a for loop, okay, in which we are defining those percentage, this percentage that I just explained to you here, 0, 25. These are the percentage. Okay, and the nearest is that, for example, if you have 2 and 3, here the algorithm automatically decide, for example, for 25% is going to be number 2. Okay, select the nearest ranked value. Okay, and then it divides the line space divides the values between 0 and 100 to the max point. I think here we selected 25 or 50. Oh, max point is 50. You see, up there it was 4. Here we have 5 points that is representative for this column. Okay, and then we are generating the models. It means we are regenerating, recreating the whole data set, but this column is fixed. For example, the column that is selected. Okay, and so as you can see, we for each fixed value of a column, we create a new data set. Okay, so here we are just calling marginal effects, and we are passing these. What it gives us here. Okay, this is the output of marginal effect. We have two arrays with two parts. I mean, so the first one is the values, the real values of the data set. These are the when we create data set, these are the values. Okay, and the second one is that the corresponding value of marginal effect to these values. For example, it means that for 2, I have the marginal effect calculated as 5, right? For 6, I have here, etc., etc. But it's not 6 because to the power of 10 or minus 2, right? That's it. So these are interpreted like this. So here we have data, and then we have the corresponding values. It goes to the end. I'm just going down. So here, just explain. So we have two arrays. The first array corresponds to the fixed values of the future sales cost, for example. The second corresponds to the mean customer satisfaction values, okay, calculated by marginal effect. Here again, I took just the above values to make sure that it's not confusing for you. So delta y here is that the customer satisfaction, which we are having the absolute values of these two. So something that I showed you in my presentation. So we had this absolute value of subtraction between yi and xi or xi minus 1. Okay, so here we have these values when this future changes from this to this. Okay. Now, here we have a problem with marginal effect. So, why? Because futures with skewed or multimodal distribution might disproportionately affect marginal effects. Okay, if fixed values are chosen uniformly. So, because here you see that there is no problem, but here we have this skewed, right? Here we have some problems. So in skewed distribution, most values are concentrated near one end, and uniform fixed points would overrepresent the less frequent values. Okay, that's the problem with marginal effect. And for the bimodal distribution, there are two distinct peaks. Here we have these two peaks, right? And uniform fixed points could miss capturing the nuance of each mode. Okay. So what can we do with the distributions? What we did is that we selected KDE, kernel density estimation, okay, for to see the to do this estimation. We are estimating of where data is concentrated. That helps to understand which region of features domain contribute most to the model. Okay, so this is the KDE's formula. And then to calculate peace, we are using this formula. From what we obtain above, y mod, okay, I just go back fast here to just remind you, delta y was the difference in the customer satisfaction, okay, when the future values change from, for example, here to here, right? So we have delta y, the absolute value of y changing, the PDF, which is we calculated with KD up there, and here we have the okay, here there is a d is, I'm so sorry, the d is missing. So because both, if you remember in the formula we had this probability to the power of d, here also we had probability of to the power of d, so both needs to have d. Okay, here I just showed you, for example, if xi, these are the real values, and let's think about this as probability density functions that calculated by KD. So basically, we are using the effect or our formula is here. Okay, in this formula, as you can see here, we have the result. Result is calculated in marginal effect up there. I just show you we have two arrays or two arrays. One is the values, and the second is the marginal effect calculated for that. This one correspond to the marginal effect values. Okay, so I is the whole the columns indexing, and one correspond to the to these values. Let me just go back. Sorry, guys. To these values, fives. Okay, the value of marginal effect. And then we have these PDF functions that calculated using KDE, and we are subtracting the values of each value in our data set. Okay, so these values, it correspond to xi and xi minus 1, these values. Okay, the first array. And we are multiplying by this to the power of d. All is to the power of d. Okay, so I rewrote the formula in order to make sure that it's not ambiguous. Okay, this is a weighting, by the way. This part is really the weighting in our formula, in this formula. And we have this probability weighting. Again, I just explain it. Just you have the comments. You can just look at these if you're interested. And for the mean, I showed you also the mean formula. Okay, so let me just show you because we are going. Okay, these are the result. Okay, if you look at this this result, first of all, I would like to bring your attention in ATE and other causal model frameworks, you only have one value, as I discussed. So we have the problem. We cannot understand when the element is more rare or more frequent. What are their impacts on causal effect? So basically, we are giving a range here, right? We don't give just a simple value. So this 0 is more rare events. Here we have more frequent events. So this is the most important part of our work. And then as you can see, for example, in mean piece, number 6 correspond to monthly usage. Okay, let's just look at up there in the data set and see monthly usage. You see, here we have the first most important element according to the data set is product need. Okay, and we deleted this one, so we ignored this one. What is the next one? Is the monthly usage. Okay, and if we go back to our result, see this one is number 6, which is monthly usage. Okay, so basically our result is evident. But as I told you, we have this rare and frequent, and we're using this mean. Sometimes when you want to see really it, because we applied this code to the cancer data sets also, and maybe you see something like this. This shows that when the data is more rare, is very important. Okay, and the more it becomes frequent, their causal effect becomes less and smaller. So here we have this value because our data set is like this, and they created, so it's just one line almost. And although we see a little tilt here, but usually if the rares are very important, you should see something like that in case you apply this code on some data sets. So basically, in different data sets, the result that you are going to get is going to be different. That's what I'm trying to tell you here. Okay, and then we have positive and negative pieces values, as you can see here. Number 4, for example, last upgrade has the negative pieces. It's the highest negative piece causal effect values in our model. Okay, and we have the also positive one, as you can see here, and well, here is really the one by one each columns. We showed every columns their mean piece impact on the causal effect. Now, as I told you, if you continue with this code, you will see these two combined variables. Okay, that can be generalized in multi variable causal effects. So this one, if you guys happy with that and would like, I can make a presentation about that one too. I stop here because it's 12:50 and I don't want to take more your time. If you have questions, I can go with the questions. Thanks for watching and attending this presentation. Thanks.